Hello everyone. So in this video, we are going to talk about augmenting data structures. So augmenting here means that we are going to add a new information in our existing data structures to give it a new meaning. So we have many data structures we have been using and we have discussed we have stack, we have queue. So for example, in our default stack data structures, we have a kind of mechanism which works on LIFO last in first out, where we are having uh, two operation push and pop, and we have one kind of variable or one indicator top that basically manages how the operations can be performed. This is the default definition of the stack, the default structure of the stack. Similarly, in the arbitraries, we are having a binary search tree which is balanced, and if you look to the node of these binary search trees, these nodes are comprising of the data elements, the link field for the left and right subtree. It also maintains the coloring for each node. Now, this is the default definition of arbitrary. Now, we can uh, look to the problem that we are dealing, and then we can use some existing data structures that is not actually to be used in the default form, but we have a realization that in the default data structure, if we add some new field, some new information to it, then it will be giving us a new significance. It will going to help us to solve our problem. So augmenting data structures is basically adding new things to the existing data structures to get some more information. So in this lecture, we are going to understand what exactly is augmented data structures, how this is to be achieved, and then we will take some examples to realize that how augmenting can be done in a real life scenario. So in our discussion, we are going to talk about order statistics tree, that we will going to create a new data structures, or you can say a modified data structures with the help of RV tree. So let's start. Okay, so let's look to some of the important points for augmenting data structures. So basically, we are using some existing data structures and we are adding some new thing to it to giving a new shape. When I say new shape, means we are expecting to get some new features out of it. So before we start augmenting in data structures, we need to understand these 4 points. So these 4 points must be fulfilled, must be confirmed whenever we are going to augment any data structures. So the very first thing is you need to identify one existing data structure. So if you are going to solve any problem, definitely you are looking for the most uh, relevant data structure that can be used to solve your problem. So you must be looking for the data structure that can best suitable to your problem. So you need to identify. So there are many instances that we come across that some data structures may be nearly close to our solution that we are expecting. So you need to identify that either is there any data structure that exists that can solve your problem completely, or there isn't data structures that can solve your problem or nearly it can solve the problem. Then you can pick that data structures that can be augmented, that can fit to your problem. Then determining additional information to be maintained. So once we have identified the existing data structure that need to be obtained, and obviously we have find that the existing form of this data structure is not going to uh, fulfill all our needs. So we need to identify that what should be added into this data structures that can uh, 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 make our job complete, or that can simplify our problem. So identify the data structures, and then also to identify that what information is missing in the present form and that need to be added. Then verify that additional information can be maintained. Now this is an important point. So augmentation basically means you are adding something new to the existing data structures, but provided that you are not going to violate the existing properties. What does it mean? It means if we talk about arbitraries, arbitraries has its own characteristics. It's a balance tree, it's a binary search tree. So when you are using arbitrary, it will remain the binary search tree. If you want to add something to it, it will remain a balance tree. If you add something to it, if you do operation like insertion a node, deleting a node, then whatever the cost of this arbitrary actually happens in the default form. So after you know when kind of modifying after adding some more in things to it, it does not violate all these properties. Means the basic, the default nature of the data structures must be remain intact. Then only the augmentation has a meaning. You can also think about what new operations can be added to this newly devised data structure, or a new augmented data structures that can ease your task. So, for example, in the arbitrary, the default operation that we talk about is inserting a node, deleting a node. In the stack, we are talking about push and pop. If you feel like that with this stack structure, I can do more, but for that I need one new operation. Okay, that you can add a new operation, provided it does not violate the default behavior of a stack, that it works on LIFO. The cost of push and pop must be a constant, constant cost operations. So these 4 points are always to be kind of satisfied, or need to be taken care when we augment any new data structure. So let's move next. In our example, we are augmenting a red black tree. So I believe that you already know what is red black tree, how we do operations in red black tree, what is the property of red black tree. This must be known to you, then only there's a meaning to augmentation of these data structure. So if you are not aware about red black tree, so you can just uh, refer to the previous lectures on red black trees and make your understanding better in the arbitraries. So what we are going to do, we are going to augment a red black tree, and we are going to devise a new data structures. Uh, let let's say order statistics tree and interval tree. So these two data structures, you can say, are devised by augmenting an existing data structures RB tree. So what exactly is order statistics tree? So order statistics tree is basically we have a dynamic set of element, and that allows us to do or get some information, like in this order statistics tree, we can easily find out the rank of any element. So the rank of the given element can be easily find out. Also, we can find out the ith the smallest element in the given tree. So, for example, if this is the tree A, let me say like this, 15, 12, and 20. So if we do in order traversal, it comes out to be 12, 15, 20. So if I want to know uh, the second smallest out of this tree, so this is the simplest tree that I have made here. Let's say this is black color, this is red color, this is red color. So this is a red black tree. The root node is black in color, and it also satisfies all the other properties of red black tree. So here you can see that if you do the in-order traversal, we find the sequence. If I want to know what is the second smallest, so second smallest is 15. So here you can see it's a very simple tree, but if the tree is large, and if it is asked what is the 10th smallest, 12th smallest, 20th smallest, then we need to find some logic. With the order static tree, it is pretty much easy to find any of the smallest element. Find the rank of the given element. Also, with this tree, we can easily find out what is the rank, what is the position of any element. For example, the position of this element 20 is third position. This is second position. This is first position. So you can just pick any element of the tree, and you can find out its position, its rank in the given tree. For example, if I want to know what is the rank of this element, that means I want to know that if I do in order traversal, then at which position this element will occur. So this operations can be easily perform. Now, this is our requirement to find either smallest, to uh, find the position of any element, and we are looking for any data structure. So there is no such data structure existing by default. So we have decided, okay, this red black tree has a property that actually matches with the requirement, and if we add some more information to it, we can get our job done. So we'll see that how this augmentation can be done. And then there's an interval tree is also there. So interval tree is basically like, describing a set of intervals. So like in the node, we keep some values. Let's say this is 15, this is 20. But in the interval tree, instead of keeping the one particular value, we are actually keeping the intervals here. And then with the help of this kind of structure, we can do a lot of information that we are going to discuss in the in the lecture when we talk about interval trees. So let us first talk about this order statistics tree. So in the order status tree, as I said that we are doing augmentation, so we will keep all the things which are there in the default data structure. So arbitrary we are using. So the default things will be already existing there. So we have the key value, we have the color value, left and link and the right link. This is already there in the default arbitrary data structures. Apart from this, we are going to add one more field that is called size field. That means now every node, apart from this information, will also maintain one extra field called size. Now, what the size basically refers to? Size basically refers to the number of elements in that tree, including itself. For example, if I see this is the key value 20 is 26, and this 20 is the size. That means this tree is having 20 nodes, including this. Now, if we take this subtree, so this subtree means we have 12 nodes, including this node also. Uh, uh, this is 12, size 12 here. So if you look at this is 3, this is 1. So this particular field refers to size. Now, how to find the size? Size can be easily find out by using this formula. The size of the left subtree and the size of the right subtree plus 1. So if you look at this, if I want to know the size of this particular node, this node is basically a root node for the entire tree. So if I want to get value 20, so how can I find out? I will look to this value 12, the size of the left subtree, the size of the right subtree. So 12 plus 7 plus 1, that is 20. So you can just check this, verify this particular calculation for any other tree. So this is again a tree. I want to know what is the value for this. So I can look at this 4 plus 2, 6 and plus 1, 7. So this is how we can find the size field in the order statistics tree. Now, apart from adding one field size x, we are also going to add one more operation. So like operation means we are doing insertion operation, we are doing deletion operation. We are also adding one more operation that we are calling as order statistics select operation. And select is basically we are trying to search any element with a given rank. So here the problem is we are trying to retrieve an element with a given rank. And rank, we discussed what is rank. Rank basically we are actually referring to the position in the in order traversal. So here x denotes to the root and I is the rank which we are looking for. So I may be asking my query like for a given arbitrary, I want to look the uh, for the 20th rank, or you can say this is the 20th smallest I'm looking for. Okay, so 20th smallest is basically if you arrange in the ascending order, then the 20th element is actually the 20th rank. Okay, so I want to find the 20th smallest. This is just an example. So how can we find out using this structure? So this is the pseudocode or the logic is given here. Okay, so look here, we need to pass the root of the tree and the position means the I the smallest I can say, or the I want the ith rank element I want to know. So I will pass this I. Now the rank is find out by size left x plus 1. So basically if you look to the structure, this kind of structure, so this, now if you do the in order traversal means you do the left traversing. So this is in order to the left node, right? This is what we follow. We keep on traversing the left side, and then once it is we reach to the leaf node, and then you can just access this node, the root of the last label sub tree, and then again you will be doing the same thing in the right subtree. This is how we process in order traversal. So because we are doing left and then node, so if you want to know what is the position of this, so you can just look to the size field here and then plus 1, that will be the rank of this, means this is the position of this element. So it will applies for every tree, you can say. For example, if I want to know what is its position, so you can just look to this rank of this left node, and then you can add one and you will get the rank of this. Rank of means the position of this element in the in order traversal. So the rank is find out by the size of the left x plus 1. Now, if you are looking for particular rank, and if this r equals to r, that means you have already done, you found the particular element of the desired rank, and you will stop, you will return. Otherwise, if you are searching for any element whose rank is less than the rank of the, now this rank is basically for the root node. Okay, so if you find, if you're looking for the rank which is less than the root node rank, or you're looking for any position element who is less than the root position, because it's a binary search tree, so all the element which are lesser than root goes to the left side, all the element which are more than the root goes to the right side. So obviously I is less than r, so we have to again recall recursively the same procedure, but now we will pass the left subtree address. So if let's say we have to move here, then we will pass the address of this node. So this is the left subtree, and we will pass this address, and then we will do in the same way. Now the point to note here is that we are searching for I, and we are moving to the left side, it will remain I. But let's say this condition is not satisfied, means the I is more than R. That means we need to move to the right subtree. But when we move to right subtree, then the rank, then this I is changed to I minus R. This is to be noted here. So if we go to the left subtree, we keep this I as it is. But if we are traversing in the right subtree, then this I will change to I minus R. Okay. So let us also look to this. What is the impact of this operation? Does it going to add an extra cost to us? So every time when we do this operation, so what exactly we are doing, we have to start from the root node and we keep on moving down. And if you look to this, what task we are doing, this is a task that we are doing is actually a constant kind of operation. And how many times we can do this operation? So we know that the RB tree is a balanced tree, so the maximum label that can go, means the maximum height that the tree can have is log n. So if we assume that we keep on moving up to the lowest label, then log n uh, times we have to do this constant work. So the overall cost of this is log n. So it is not going to uh, charge some extra cost to it, and we are able to uh, keep maintain all the cost that is provided in the default structure, that is a default arbitrary. So let's move to the next part. Now let us understand that how actually we can find the element of the given rank. So here if I want to find the 70, the smallest element, okay, or I want to find the element with the rank 17, this is the same meaning. You can say 70 the smallest element, or the element with rank 17 you are looking for. Then how do we can proceed? So you can see here our key value is 26 and our I is 17. So first we find out what is the rank of this particular. Now this 20 is not the rank. 20 is basically is a size. Okay, so if I want to find the rank of this node, then I have to look to the left subtree and I will look to the field size. So field size is 12 and 12 plus 1 is 13. That means the rank of this node is 13. The other meaning of this is that if you arrange the items in sorted way, then this element comes at 13th position. So we get rank is equals to 13. And here that the key is 16, the 17. So uh, what we will do, we will find the rank of this. So rank of this comes out to be 13. So rank is less than I. So if the rank is less than I, then we have to move towards the right subtree. So you can see here, if the I is less than R, then we go to left. If the rank is less than I, then we have to move to the right. So whenever we move to right, we find a difference. So we will find the I minus R. So that is 17 minus 13 is 4. So that means we move to the right subtree. So this is our new problem to explore. So now the key value is 41 and the rank that we are looking for is 4. So we start with this problem 26, 17. Now this problem has been changed to 41, 4. Okay, now we are here. So we'll see that what is the rank of this. So if the rank of this is 4, that means we are done. We have to stop. So let us check what is the rank of this. So we look to the left side, left subtree. It is 5. So 5 plus 1 is 6. So the rank of this is 6. Now you find that now the rank is more than the I, or you can say the I is less than the R. So we can go to the left subtree. If we find out that the rank of the node is actually more than the I, so we will, and we move to the right side. So now our new problem is 38, 2. So whenever you move to the right subtree, you keep changing the value of I. If you go to the left side, then the I will remain the same. So now you are here at 38. Now you have to see what is the rank of this element. So you look to the left, its rank is, and this is size is 1. So 1 plus 1, 2. That means now you have achieved I equals to R. And then you will stop here, you will return this element. That means 38 is the element whose rank is 17. So don't forget that we are looking for the element with the 17th rank. So 38 is the answer. So this is all the steps that we did, and this is an explanation that how we achieve to this particular element. Let us take one more example. Okay, now this tree is given to us, and this is a order statistics tree. This is actually order statistics tree, which is achieved by augmenting the arbitrary data structure. So here we want to find the 7th smallest, or we want to find an element with the rank 7th. Okay, so we start where the key value is 17, and we want 7. So let us make this table to make it simpler. So key is 17 and the I is 7. So we'll find what is the rank of this element for this node. So rank of this is, we will look to the left subtree, 7 plus 1, 8. So the rank is 8 here. And we see here that I is less than R. So whenever the I is less than R, look at this, we have to move to the left subtree. So we move here. Now, in the second step, the key value is 14. I is 7. So this is actually 7, because this I will not change. We are looking for the 7th smallest. So I remains 7. Now what is the rank of this? So we look to this 4 plus 1, 5. So this is 5. So now here this condition is not satisfying. That means we have to go to the right subtree. So actually we are going to move here. But what is the new case that we take? So this is 7 minus 5, which is 2. So here we will find that actually this is the scenario 16, 2. This is what we started with. Now we are reached where 16.2. That means this is the key value 16, and we are looking for 2. So let me make it 2 here. So this is actually wrong information here. Let me update here. We are looking for I equals to 2, and so we have find 2 here. That means this is no need to do, and we are done with our answer. We have find the 7th smallest. Okay, this is not required. So let us verify that is this the seventh smallest among the given sequence. So if you write the in order traversal of this, so let me write. So this will be 3, 7 is 19, then right 20, then we have the left is done 21 and 21. So this is the sequence that we get after doing in order traversal. Now we are looking for 7th smallest. So this is 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4. Let me write here 1, 2, 3, 4, 5, 6, 7. So 7th smallest is 16, and this is what we get here, and this is our answer. So I believe you have understood how to find the any element of the given rank. Okay, so let's move to the next part. Similarly, we can also augment our arbitrary with one more operation that can be helping us to find the rank of any given element. Now, in the previous uh, operation, what we are doing, we are finding the element with the given rank. Now we will find the rank of the given element. How does it make a difference? Now, if I want to know what is the rank of 20, this is one question. Okay, what is the rank of 20? So this is rank of the given any given element we need to find out. This the earlier case that we discussed is I need to find out any element at rank 7, so that we will be doing the operation we have just discussed. So now this we will be discussing in a separate video, that how to get all this information by adding a new operation through the through the augmenting our arbitrary. So we'll be discussing in the next video that you can find. I will give the link for that video as well. So let us first talk about our previous case and move to the next part. Now let us understand that the augmentation that we did, that is we have used our arbitrary for augmenting it, and then we have add one field called size. We add one operation called os select. So these are the two things that we have actually included or added in our default arbitrary. So when we add these two things, we are able to get some extra information, which may be of our use. So let us see the impact. If I going to add these two things in our existing tree, does it going to violate any of the existing arbitrary properties, or does it impact on the running cost of any operation? For example, we are doing insertion operation, we are doing deletion operation. So by adding these things, does it have any impact on the default cost? Let us look to here. So insertion we are doing in two phases. The very first phase is what we are doing. We need to search, because we are doing inserting. Insertion is always happening at the leaf node. So we start from the root node, and then we keep on moving either left subtree or right subtree, and find the relevant position where the new node can be inserted. So in the first phase, we are just traversing from the root to the leaf and find the position for the child. The second phase goes up the tree, changing the colors. So if you remember that how we are doing the arbitrary insertion, so the very first thing is you need to add a node as a leaf node, keeping its color as red, and then we will check that still the arbitrary properties are maintained or not. So we will check for four properties: that root node must be black, the red node must have a black child, and the black height property must be maintained. So after adding this new node, there's a possibility that any of the properties get violated. So in order to fix or to get our arbitrary back, we will be actually changing some colors or doing some rotations. So first phase is inserting a node, and second phase is basically doing some rotations or changing the colors to fix it again. So let us talk one by one what we are doing in the first phase. So in order to maintain this augmented arbitrary, means the order statistics tree that we are calling. So augmented arbitrary we are calling as the order statistics tree. We are giving a new name as we have derived a new data structures. So increment size. So what we are going to do, so this is our kind of tree, and as we said that in the first phase we keep on moving down to search for the position where the node to be inserted. So when we keep on moving down, we are actually reading every node. So by reading every node, we also increment every size. For example, this is a node which have some size value, which is a node which has some size value. This is a node which has some size value. So while going down towards searching the position for the insertion, every time we are also incrementing the size plus one, the size plus one, the size plus one, because we know that if we are following this path, then definitely the node is to be inserted somewhere in this path. So when we find that position, we make the size equals to 1. So earlier, the node which was actually the leaf size 1, it becomes 2. Similarly, we have added to every node in the corresponding path by 1. We have already increased the size by 1. So we are able to maintain this size, kind of field, and without doing some extra work. Extra work, yes, we are doing some work. We are updating the field, but we are not doing the extra traversal. Along the path when we are moving, we are doing this job. So actually, this is a kind of constant effort we are doing, and we have to maximum time that we are doing this job is log n, because we have to start from the root and going to the leaf node. So there is no extra kind of cost or burden of the cost that actually incurs with updating this field. So it will still maintain log n. So in the first phase, it's okay. In the second phase, what is going to happen, as we discussed, that we are going to either change the color. So we have three cases are there in the red black tree. So if it is case one, we are simply changing the colors. Otherwise, we may be doing rotations. And rotations are to be done, that is maximum two rotation. We know the property of arbitrary, that in arbitrary we are doing maximum two rotations to fix the tree. Like in the avial tree, there might be many rotations are required in order to fix it, but arbitrary has the beauty that maximum two rotations can fix your arbitrary. Now rotation is a local operation. It invalidates only the two size field in the node. So how do we maintain the size field if we are doing rotation? Because rotation is going to change the structure of the tree, and when the structure of the tree is going to change, then definitely it has an impact on the size field. So how the size is going to be maintained? So again, we will understand this. So actually, when we do rotation, so if this is a tree, this is a tree, let's say this is our tree, and let's say you are doing rotation, let's say you are doing rotation at this part of the tree. Okay, you are doing rotation here. Then if you look thoroughly this particular operation, so normally we call it x and this call it x y, means the parent and grandparent. And this is, now this is happening, I think this is something happening when you are here, new node is inserted here, or new node is inserted here. Okay, if it's inserted here, then this is case 2. If it's inserted here, this is case 3. So in both the cases we are actually taking care of the parent and the grandparent. So the other entire tree remain untouched. This is not going to have any impact. And also, if you look, only these two nodes, X and Y, are getting impact of the rotation. Means this is going to change its position. Means the new structure that we get has only impacted these two node. And the field property means the size, the size field, I should say, that the size field of these two nodes are going to affect. So that means whenever we are doing rotation, we need to only do some extra job for these two nodes. That means it's a kind of constant work. We are not going to do it for every node. Okay, just two nodes we have to do our operation. And what operation we are doing? We are just setting the two fields. So we need to only set the size field for these two nodes. How we can going to do this? So if we are doing left rotation, then the size of x will given to size of y, and the size of x will be the left size of x plus left size of y plus 1. Similarly, if we doing the right rotation, then the things are happening in the reverse way. So let us understand in a better way. Let's look to some example that can give us a more clear picture. So now look at this. This is, let's say, some portion of our arbitrary. This is also some of the part of the arbitrary. Only we are focusing on the part that is actually getting impacted by the rotation. So let's say you are going to rotate. This is right rotation you are doing. So when you do right rotation, actually you are going to get this kind of tree. And if you do left rotation at x, then you are going to get this kind of tree. Now, so how can we maintain the size field? So here we are focusing how to manage the size field. So we are going to use this. So uh, when you are going to rotate, then this is going to come at the root. So we are assigning y, size of y will be assigned to x. Size of y assigned to x, that means x becomes 19 here. You can see here. And the right of means the size for the right child of x and the size for the right child of y. So you add these two field. So 7 plus 4 and plus 1 will be given the size here 12. So you can see here this is becoming 12 here. So I think you understood. Let us look in a different perspective when we are doing left rotation. So when you do left rotation, let me clean this all. So when you do left rotation, this is going to come down, this is going to get up. So the size of x is to be given to y. So size of x is given to y. So now y is going to become 19. Okay. And what about x? So we will look to this. The left of x and the left of y and the left of x, we will add this and plus 1, 6 plus 4 plus 1, 10 plus 1, 11. So left s, left y plus 1, 11. So you can see that x will come here and it becomes 11. So I hope you understood that how the size field to be maintained. So we have seen as overall when we are in the first phase, means when we are moving from top to the leaf, we are doing a constant effort, and then we in the second phase when we are fixing our arbitrary, then also just two nodes we need to set this property and we are done with, means this particular os select operation is not going to violate the cost of our existing arbitrary. So this is a perfect augmentation of arbitrary. So you can see here, this is one tree given to you, and you can just and we are going to rotate, right, rotate t3. So we are going to rotate here, and now you need to find out that what is the impact of size of x and y. So first you find the x, y, and then size x, size y. This is leaving to you for as an exercise. Okay, so looking to the next, let's look to the time complexity. That what is the time complexity of insertion and deletion in a newly augmented data structure, that is the order statistics tree. So we know that at the case of insertion, we have already discussed that two operations we are doing and two rotations we are doing, and that two rotations may impact any two nodes that can be easily handled by doing a constant set of operations. Okay, so we are actually doing only constant additional time we are spending to do some extra effort in order to maintain the new structure. So it has not going to violate, it was not going to change the running time of insertion operation. So insertion operation of the new trees is still log n. What about deletion? Now in deletion, again, we are doing in two phases. So we are going to delete the node. So what we are going to do, again, we will be moving in the same way as we do in insertion. In insertion, when we going down, we are incrementing the 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 size field by one, because a new node is to be added. But now we are doing in reverse. When we go down, so we start from the root node and we are searching for the node that need to be deleted. So we need to keep on moving in this way, and we are also decrementing the size field. So again, we are able to manage the size property, and we know that the effort is almost constant, does not actually going to change the actual log n cost that we say. So in the first phase, we are going to decrease the size by one. In the second phase, actually, when the actual node is deleted, again, there is a kind of double black may come and we need to do some rotations to fix it. And we know that maximum three rotations are required to fix our RB tree. So we know how to do these rotations, and the impact of the rotation is only on the two nodes. So we will use the same strategy to set the size field as we discussed in the insertion case. So we have already know that setting this kind of size field for the two nodes is again a constant operation. So as a whole, when we talk about insertion, when we talk about deletion, the cost remains log n. That means the new data structure that we have derived out of arbitrary order static tree is actually maintaining its default properties. It is actually working in the default operation. It does not change the insertion. It does not change the cost of deletion, because it is the requirement of the augmentation. When you are augmenting any data structures, is a requirement. The default operation cost does not need to divert or vary. So it is not varying, and we are done. Okay, so that's all for this lecture, and I believe that you understood what is actually augmenting data structures, and also you have understood this example completely, that how this order static tree can be achieved by augmenting the arbitrary. And also we have verified the four properties. Now this is must. You must be very much make sure that all the four properties which are required for augmenting any data structures must be satisfied, and we have seen that it is fully satisfied. So this is all, and in the next we will take some more example, and also in the next video you can see the example for finding the rank of any given element. Okay, that's all for this lecture. Thank you very much.